So the other field that we want to go ahead and discuss explicitly when talking about the electric potential is moving around in a field due to point charges. Again, knowing how the electric potential relates to the electric potential energy, we can start by thinking about the change in the electric potential energy of a test charge as you move it around in the electric field due to another charge. And so that's given by this equation here, right? So the change in this, again with U, is the electric potential energy, is equal to, there's K, I've got two charges here, and then this term in parentheses, the 1 over R final minus 1 over R initial, where these two R's are defined to be distances between the charges. So what's the distance between them initially? What's the distance between them at the end? Well, I know that the change in the electric potential is equal to the change in the electric potential energy divided by the test charge. So if I rewrite my Q1 and Q2 as Q source and Q test, right, where one of those is what's causing the field, the other one is the charge that I'm moving around in the field, the test charge is going to cancel out. And so I'm left with an expression that tells me that the change in the electric potential is equal to, again, Coulomb's constant K, but there's simply one charge here, the source charge, and then again, here's this term, 1 over R final minus 1 over R initial. Now we need to redefine what these two R's mean because they're no longer a distance between charges because we only have one charge now. They're actually the distance from our source charge to a point in space. So Ri says, what's the distance from your source charge to where you are initially? Rf is what's the distance from your source charge to where you are at the end. So as you move from one point to another, from some initial point in space to some final point in space, I care about the distances from my source charge to those 2 points. Well, again, if we think about this term, as we said before, if you've moved away from the source charge, so that would mean that your final distance is greater than your initial distance, then 1 over your final distance minus 1 over your initial distance is actually something that's negative. So if the term in parentheses is negative, then that means whether or not the electric potential is increasing or decreasing depends not just on this term, but also on my source charge. So if I have a positive source charge, moving away from the positive source charge is going to give me a positive K, positive Q, and a negative term within the parentheses. So moving away from my positive point charge is going to decrease the electric potential. If, on the other hand, I'm moving towards my positive point charge, then this term inside the parentheses is actually going to be positive. My final distance is now smaller than my initial distance, so 1 over my final is actually larger than 1 over my initial. And so my term inside the parentheses, if I move towards the point charge, is actually positive. And so I'm left with positive K, positive Q for my source charge, and positive term inside my parentheses. So the electric potential increases as I move towards a positive point charge. On the other hand, if Q is negative, then just the opposite occurs. If I move away from my point charge, I know the term inside parentheses is negative, but Q is also negative. Those two negatives cancel, and so it tells me that moving away from my negative point charge actually increases the electric potential. As I move towards my negative point charge, just the opposite occurs. So again, now I've got a positive K, negative Q, and moving away means that I actually have a positive term inside my parentheses. So the electric potential decreases as I move away from a negative source charge. Well, so we can go through the process in terms of thinking about the calculus to get this equation as well. So if we start with our definition for what the change in the electric potential is, right? So that's negative the integral from some initial position to some final position of the electric field vector dotted in with our infinitesimal little steps dr. And so if I have a point charge, and again here let's just assume that I've got a positive point charge sitting here, so the electric field points away from it. But as I move farther and farther, the magnitude of the electric field changes. So it points away at both my final point and my initial point, but it doesn't have the same magnitude. So the fact that it doesn't have the same magnitude means that unlike in the constant electric field where I could pull E out of the integral, I'm not going to be able to do that here. So instead, I just need to go through this process, and again, I'll deal with the dot product first, and I'll choose to move in the direction of the electric field so that dot product is positive. And now to calculate the magnitude of the electric field due to a point charge, I know that's just kq over r squared. And the k and the q, those are constants, and so I can pull them out of my integral, and so I'm left with negative kq times the integral from some initial position to some final position of 1 over r squared dr. And the antiderivative of that is negative 1 over r. The negative for my antiderivative cancels the negative sitting out front. I evaluate my integral final position to initial position, I end up with exactly the same equation. So either way I get there, whether by starting with the change in the electric potential energy and then dividing out the test charge, or starting from my definition for the change in the electric potential and going through and deriving using the calculus, either way I get the same equation. Now, again, we'll often want to talk about the electric potential. And again, the electric potential really means the electric potential relative to the point where the electric potential equals 0. So we just need to figure out where that is. So for this equation, to calculate the electric potential at some point in space in the electric field due to a point charge, I'm going to be able to use the electric potential V is equal to kq over r. Q is my source charge, and r is the distance from my source charge to the point P out in space. Okay? So Q and R are very clearly defined here. But looking at this equation becomes, so V becomes smaller and smaller as I make R larger and larger. And so what we do is we say the 0 point, if we want to talk about the electric potential, the 0 point for this equation is when you're infinitely far away. So the electric potential equals 0 when you're infinitely far away from your point charge. When we talk about V is kq over r, what we're saying is you can calculate the electric potential at some point in space in the electric field due to a point charge, but that electric potential is the electric potential relative to a point infinitely far away where the electric potential is 0. So some important points to make about this equation. So the first one is that, again, r is defined to be a positive distance, right? So then whether your potential is positive, negative, or 0 depends on a couple of things. So your potential can be positive if your charge is positive. So k is always a positive number. R is defined to be a positive distance. So V will be positive when Q is positive. It will be negative when Q is negative. It's going to be 0 when you're infinitely far away, right? So that's how you make V 0, is you just go infinitely far away. So the potential, the electric potential, it can be positive, it can be negative, it can be 0. It's clear in this equation that the electric potential only depends on one charge. Just what's the source charge, what's the point charge out there that's creating the electric field that you're moving around in. This is like the electric field that, again, only depended on the source charge. And like the electric field, again, what we're really talking about is as we move around between points in space. So the electric potential, like the electric field, was describing what's going on in the space around your charge. Notice that we don't take the absolute value. So that was something that we did when we were calculating the magnitude of the electric field, is we took the absolute value of Q. We don't do that here, right? If Q is negative, we plug it in as a negative number. That gives us a negative value for V. 5. When we calculated the electric field, that went like 1 over r squared. Here, the electric potential as we move around in the electric field due to a point charge goes like 1 over r. So you want to make sure that you've got the right power of r on the bottom of your equation. It's an easy mistake to make, and so an easy way to throw away points is just you have r squared rather than r, and that's not what you want if you're calculating the electric potential. And then 6, the last important point to point out is that, of course, the electric potential is a scalar. It's not a vector. And why do we like scalars? Because they're so easy to add. We don't have to worry about all the infrastructure in terms of adding together vectors. So that what that means is that if we have multiple point charges that are contributing to the electric field, then all I need to do is calculate the electric potential at some point due to each charge and add them together. So if I'm going to calculate the electric potential at a point in the presence of multiple point charges, so here I've got Q1, I've got Q2, I'm interested in the electric potential at point P, and so again, this is really the electric potential at point P relative to the 0 point infinitely far away. then I've just got two terms. I've got the contribution from Q1, I've got the contribution from Q2. And so I'm going to have KQ over R. I'm just going to have it twice. Once to determine the contribution from my first charge, the other to determine the contribution from my second, and I just add those two things together. They're scalars, I just add them together as numbers.